In this video, we are going to look at several ways to represent complex numbers geometrically and ways to give the complex numbers some sort of physical significance. So a very common and important way of representing a complex number is simply as a point in a two-dimensional space. The one thing which is a little different from the two-dimensional graphs with which you are probably familiar, the horizontal axis we are labeling x, so you're probably familiar with that, but we're going to label the vertical axis as I. So we call this the imaginary axis. X along here is the real axis. The vertical axis we call the imaginary axis. So this we call the Argand plane. So we can represent any complex number as simply a point in this plane. So one of the important things about this is we know that this particular point has certain coordinates. So if we go a distance a in this direction, so we go a units east on the x-axis, that means that the x-coordinate for this particular point is a. On the other hand, we can go vertically in the I direction a distance b. So we go b units in the I direction. So therefore the second coordinate is going to be b. Therefore, we can think of this particular complex number as simply being the ordered pair, a point, in a two-dimensional space whose first coordinate is a, that's the distance along the x-axis, the real axis, and the second coordinate is going to be the distance in the imaginary axis, b. So we often think of this point as being synonymous with this ordered pair AB. But it becomes even more useful to that, if we like, because in addition to thinking of this particular complex number as being a point, we can also think of it as a vector. And the kind of crucial idea here is we draw a line in this particular direction. And we can think of it as the resultant of adding a vector in the a direction. So we have this vector a, which goes to the right. And then we add to that a vector going b units in the imaginary direction. So therefore, this particular blue line that we've drawn here is actually the sum of two vectors. And this is the vector a plus bi. So here we've gotten a physical significance to the idea of writing a complex number as this particular sum a plus bi. Now to continue with the representation that we've used before, in addition to thinking of it as going a units along the real axis plus b units in the imaginary axis, that's one way to think about it. But we can also think about it as going a particular distance a plus bi, or let's call this distance r. So we can also think of this particular length as being r. And we've actually rotated this particular vector an angle theta from the horizontal. So this gives us the significance when we've written a complex number as r times e to the I theta. The r is this particular length here, the hypotenuse of the triangle, and the theta is this particular angle. Now what's not clear is how this particular expression gets converted mathematically into the a plus bi expression, and that's going to be shown in the next video. But for the time being, we can just at least realize that if we write a complex number in this form, the physical significance of the r number is at a particular length, and the theta tells us an angle, so effectively gives us a direction for a vector. Now we'd like to look at another very useful way of thinking about this particular point z, the complex number, and the vector that we represent by this particular blue line and by the complex number z. Continuing with what we had shown before, let's consider the length of this particular vector to be r, and let's also consider it to be made by rotating a particular angle theta from the horizontal real axis. Now, once we have that, we can use trigonometry. And we recognize that the leg along the real axis in the x direction actually has a length of r cosine theta. So this particular vector here, so I'll kind of emphasize by making it orange as well, has a length r cosine theta. On the other hand, the length of this particular leg, which we'll draw in purple here, is going to be r sine theta. So now we have come up with another way to think about the coordinates of this particular point. Because the first coordinate, so we have our point z, so right here, its first coordinate along in the real direction is simply r cosine theta, and its second coordinate, essentially its height, is going to be r sine theta. And it's going to turn out, even though it seems very complicated at the moment, that this particular way of representing a complex number is going to be extraordinarily useful for us. And in fact, we're going to be able to interconvert the various different representations for complex numbers to use the version that's easiest in a particular problem. But for the time being, I thank you for your attention. Have a good one. Hello. In this video, I'm going to show perhaps the most useful way of interconverting representations for complex numbers. Let's assume that we have a complex number z that we've written in the following form: e to the I theta. Now this is a very strange type of a representation because we have e, which is a transcendental number. It has an exponent that's actually an imaginary number multiplied times an angle. So we would like to be able to write that in something a little more useful for us. It turns out, thanks to Euler, we can write it in the following form. So we can write it as cosine of theta plus I times the sine of theta. And this very important representation is called Euler's formula. You might recognize that this looks very familiar to what we did in the previous video, where we noticed that the sort of x-coordinate of our particular complex number, it had a length of cosine theta multiplied by r, but in this particular representation we're assuming that r is equal to 1, and that the height was I times sine of theta. So if we wrote it as an ordered pair, we would write it as the ordered pair cosine of theta, sine of theta. And in our particular course in quantum chemistry, we're going to need to interconvert these particular two forms all the time. So that's incredibly important. We also notice that one of the ways that we use to represent complex numbers is of the form a plus bi. And recall that when we did that, we're assuming that a and b are both real numbers. So through Euler's formula, we can actually write an explicit form for a and b. So we see that a, which is the real part, is going to be cosine of theta. That's the real part. and b is equal to sine theta. And if we have I times sine theta is going to be the imaginary part of the complex number. For the sake of convenience, from now on, whenever we write a complex number, we're going to write it in a very, very slightly different form just to make it easier to write. Knowing that theta is an angle, we can use any symbol we like to represent the angle. So by convention, in quantum chemistry, we tend to write, instead of using theta, we just use simply the variable x. So instead of writing e to the I theta, we're going to write e to the ix, which means exactly the same thing. It's just easier to write, and that's typically what chemists will do. So if you want to write Euler's formula to apply to our expression now, it's simply going to be cosine of x plus I times the sine of x. I thank you very much for your attention. Have a good one.